Dankeschön. Ich verstehe Deutsch, aber spreche nicht, so my presentation will be in Franglish. I hope you will follow me. So, it should be a borderline presentation. I'm not a specialist in climatology, but in data mining and complex system analysis. And I will apply some creative thinking on IPCC models. It will be at times provocative, and so I hope some reactions and discussion later on and maybe pushing the light forward. So, do you know this man? He's a wise man from Central Asia, a free spirit. Nasser Eddin is his name, a free spirit, very critical against the authorities, making jokes about them, ridiculize them, demonize them, and that's what I would like to do also. He's a model for me. I spent a lot of time in Uzbekistan trying to develop that country. I'm an honorary professor of the Academy for State Reform and Modernization there, and we, together with the local team, we improved the GDP of that country by 8.5% a year, which is one of the highest in the world, comparable to what happens in China. And so this is a model for me, and it will be our guide through my presentation. Okay, so we know that IPCC models are wrong. Quickly, I recall that. Mr. Taylor presented you this story already, the classical scientific method that we try to use, and then the IPCC method, where we start from a political agenda, build up some theory on unproven hypotheses, make cherry picking with the data, and say, yes, this is the truth. And it's the truth because we have consensus, and this consensus is reached by 97% or 99% of the scientists. The only problem is that the scientists are 2 or 3% of the survey, and it's not 100% clear that all of them believe in the theory. So the postmodern approach, I said what I think about it, and the consensus, flies of consensus bullshit, not scientists. Sorry, this is maybe a little bit rude. So let's go to the next slide directly. So the key problem, I think, from IPCC is that they focused on that highlighted part of the curve where indeed you have some apparent correlation between anthropogenic CO2 emissions and the temperature anomalies. I think it could be maybe a side effect of the ban on CFCs and aerosols that are important for the cloud formation, as Professor Zenmark will show us and recall us later on. So they afraid us with that. Save the planet, hurry up, it's urgent. You developed guy are guilty for all that, you have to pay for it. Carbon taxes and other mechanisms, that's the story. You must make sacrifices to save our goddess Gaia, the earth, a new religion. That's the story. And then come the hard facts, the fact that the projections don't fit the measurements and that the gap increases with time. You know that already. This is a graph, the conclusion of an EIKE meeting 3 years ago already, saying it's not linear. You have to work with take into account the natural cycles, and the dispersion of the models is the same since 30 years. It cost a fortune. It cost a fortune in computers and no improvement in 30 years. Now, what happens? Well, if you discover that you make mistakes, what do? Should you change your mind? No, just hide it for a while and wait what happens. Okay? That's what they're doing. Okay? Now, what went wrong with IPCC models? For that, we need to enter in the climate wonderland of the IPCC rabbit hole, and we will do that. And something went wrong at the real beginning, I'm afraid. And I have here a few items that I would like to discuss briefly, because each of them could be a full presentation. Four things. They forget the natural cycles. They suppose that there is a constant solar flux. They suppose local equilibrium at each point on the Earth. I think you need to understand the structure of a complex system before trying to tackle its dynamics and making projections, not to call forecast. Correlation is not causality. And there is confusion between random noise and chaotic noise. And that's a point that I would like to develop a little bit, maybe. And then you have calibration problems and errors of the data that you use for calibrating that. But that's the topic of the presentation of my friend Michael Limburg, and I wouldn't develop that too much. So let's start with four things. You know it, huh? For them, the radiative effect is the most important one, and everything around it needs to be used as a tuning system. And what they did was working on a linear feedback system in such a way that the formula becomes this one. Delta T is the change in temperature. Delta R is an important parameter. It's by how much can you increase the temperature if the concentration of CO2 in the atmosphere doubles. And 1 minus the sum of the four things is the tuning button that they try to use. Now, the forcing, initially, you see it was around 0.6, 0.7, but the latest results push that downwards to quite zero. Here are the data. It's the value of that delta R as function of time, and you see that the publications come to conclusion that this diminishes more and more and more, and finally, at the end, we are not at the 3.5 degrees about which IPCC is talking about, but a fraction of a degree. So this means also that the target of 1.5 degrees centigrade, we will reach it even if we do nothing, because the climate is like that. But okay, nobody is perfect, and the IPCC is far from perfect, of course. So there are hidden hypotheses with forcing, and here comes the problem. They are linear, proportional to temperature, independent from each other. They are just additive, they don't interact. They are instantaneous. Well, we know that we have a lot of constant times in the climate system. They remain constant over time. And they forget about cloud coverage change and some long-term periodic components that we have. There is no amplitude modulation in the system too. No frequency modulation. Okay, and I would like to show you that, well, does it matter? Or is it just some nasty critics of some nasty guy somewhere in a corner? Or does it matter really? Well, I will try to show you that with a very simple example of a non-linear equation, which is a classical one in nonlinear mathematics. It's the logistic equation. It's about 150 years old or something like that. But it's interesting. So you see, it's a product of a positive feedback and a negative one, xt and 1 minus xt respectively, and a tuning parameter A. Now what happens when we change that tuning parameter A with this simple equation? It's a parabola, just a parabola actually. Well, if you start with very low values, it's evanescing, it's going to zero, and you have a decreasing trend line. If you increase that parameter, you go to an asymptotic value, different of zero, and you have now an increasing trend line. Let's continue a little bit further. Oh, it starts to oscillate before reaching that equilibrium point, but it's dumping out, and it reaches that point. And we increase a little bit more that parameter, and now it continues to oscillate, and it never reached that asymptotic point. We say it reached a final loop around a kind of attractor, actually. And if you continue, the amplitude increase, and more, And at a given moment, what happens, oops, sorry, I had to come back. Can I do that? No, I cannot come back. At a given moment, you have a modulation of the amplitudes of the signals. Now I'll go further, and here the system becomes chaotic, as you see. And I change the parameter by 5, 10 exponent minus 4. And you see the difference of the curves. For the first one, I have a positive trend line. For the second one, it's quite 0. And if I tune it a little bit further, it should become negative. Okay? So what means a trend line for this kind of signals? We can ask ourselves that question. Okay? So you see amplitude modulation, and you see from time to time quiet periods of time where it doesn't oscillate at all. For a very deterministic, simple equation. Huh? Now, if you try to put that in graph as function of that parameter A, you obtain something like that, something stable, asymptotic value, and then you have here bifurcations, that's the words we use to define a change in attitude. And you have apparition of harmonics and subharmonics at that level, and amplitude modulation a little bit further. And here you have still some deterministic moments from time to time, but it's chaos there, which means unpredictable. Now, that's a nice story, but is this relevant to climate or not? Is the climate chaotic or not? If it's chaotic, it's unpredictable, at least at a few decades or centuries, as IPCC is doing. Well, I took 2 examples. Sea ice extent, and you know what happens. You see, first you see that there is some amplitude modulation, and the alarmist will say, "Oh, look at that! The ice is melting. What a disaster!" And when it's stable, they would hide it and come to another topic, extinction of bears, or I don't know what, or the level of the ocean that comes up. But that's the story. Look also at the trend line. I don't know what you can take out of that. But that's what they're doing. Now, this is a figure from Professor Ludecker. It's a scalogram. It shows as function of time the importance of the harmonic, the periodic components in the signal. And how darker the color, how stronger that signal. And you see that, what do you see? Well, you see that from time to time some frequencies are very high, and we find back the 60 years and 180 years cycles in this data. But if you look at, having in the mind what I explained just before, you see that when the signal is very strong, you have actually bifurcations. It splits in harmonics and subharmonics, which is another indication that the system is probably chaotic. That was for the forcings, and the fact that the forcings are not linear could be of importance, and they are important in climate science because you see that you have chaotic signatures. Now, I would like to go over to a second topic, which are global temperature anomalies, also very basic in all the story of IPCC. Invented by the World Meteor Organization. You take the average over 30 years, and then you see how the temperature in a given spot change with time. Hypothesis, over 30 years, the temperature remains constant, of course. It's approximation by an horizontal value. We know that we have a lot of periodic components in climate proxies and temperature. And they cut there, 30 years. It goes from one day and night, up to the Milankovitch cycles and maybe above of hundreds of thousands of years. They cut there. So they're in some situation where, in fact, that averaging period that they take as reference is comparable to some of the periods of the signal. Now, this is some evidence that you have more or less long-term differences in temperature. This comes from Professor Ewert, in fact. And he showed that in different locations, the temperature increase is stable, decrease, etc., in a cyclic way, but not periodic. The periods change, and not in phase. It changes from point to point at different moments, as you can see by this color code. Okay? nonetheless, they do it again. Now here, I take a sinusoid of 360 degrees. And let us suppose it's 180 years, so 2 degrees is 1 year. And the red horizontal bars are averaging periods for calculating anomalies. Now you see I represented 3 situations. The first one, you are close to the top of the sinusoid, and the anomaly will be as the top figure on the right side, increasing, but slowly less than linear. In the second situation, it will be decreasing and even become negative eventually compared to the basic line. And in the third one, you reach a bottom, it will come up. And all this for a given signal, which is perfectly horizontal, perfectly constant. So this is fake, of course. Anomalies, what you can deduce from anomalies is fake if you have cyclic signals like that. Now, I have a fun story about that. You know about the sun and the moon. You know the moon plays a gyroscopic effect that makes the fact that the axis of the Earth is not tilting as much as for Venus and Mars, which is good news for stabilizing our climate. And also you know that it plays on the tides. But maybe if it's able to move liquid, it's also able to move air, and you can find some trace of it in temperature data. Now, generally people take monthly averages, and the length of a moon cycle is 28 days. Now, if you take, I took here some local data from Uccle, which is the place where I was born in Belgium, it's beside Brussels, and you see indeed that you have fluctuations, not with 28 days, but 14 days of the period of it, which is probably linked to the position of the moon towards the sun and probably some gravity effect hypothesis. Okay, we see that. Now, if you average over the month, you will have problems there. This comes from Frank looking at errors, and I think Michael Limber could speak about that maybe also in his presentation later on. They come to the conclusion that this induces an error of about plus or minus 1 degree if you average over a month and don't take account of it. But I'm interested in that cycle of 28 days. And here we have a problem. If you make a monthly average over 31 days, year after year, the phase of the moon at the beginning of a month will change. So the contribution of the moon signal will change from year to year. I put here some well-known data about cyclic components in climate, and I made some simulation. You see it on the top, and on average, of course, I obtain the well-known figures, which is normal. I put the annual cycle in it. But if you zoom in, and if you look at the temperature in detail, you find something strange. With a little bit of imagination, if you remove the strong El Nino and Pinatubo events, instant events that happened on the top left side of the figure, where you can find back the hockey stick of Michael Mann, and the pose, and even the mini ice age that is predicted by some. Just because, well, the moon has a cycle of 28 days, and we average over 31 days. Above on the left, you have a real figure. That's discussed and discussed on the website of climate-sceptic websites. And under that, you have some anomaly simulations for different months along the year. It's not exactly the same because I was not patient enough to go up to the end, but there is some similarity, no? So this may be an explanation of anomalies. In any case, it's worthwhile to be analyzed, I guess. The same applies for linear trends and cycling signal. If you have a single sinusoid, according to the initial phase of your sinusoid, where you start the calculation, the trend line can be negative, positive, or zero. You need at least 5 or 6 sinusoids to be out of that. It is induced some bias according to where you start also. No, okay, that's theory, that's a subject. What about real climates? Well, you know this figure. It's one of the classical figures from satellites. And if you start the starting moment and change the length of the window, look at the dark lines, which are the trend lines. It decreases, it increases, it decreases, it increases. And here you can even find some different steps if you want. All that with the same data. So the importance of the window measurement is something very important, often over-neglected. And so, you need at least 5 or 6 cycles, but as you have continuous cycles from one day to hundreds of thousands of years, it's very bad news for looking at linear trends in signals, of course. Yeah, even more, this is used by alarmists to say, look what happens, the temperature increases faster and faster and faster, just because they're on the ascending branch of a sinusoid and they take different windows. It's a fake conclusion again. We knew that since 3-4 years. Now, something else interesting, it's about correlation and causality, which is a little bit philosophy, but I present it not in a philosophical way, in an easy to understand and joke way. First, you have spurious correlations linking things, apparently, that are completely not connected, like this one. Nobody has no doubt that this is not connected, of course. I have a collection of this kind of funny things, if you want. Also, this is interesting. Did you know that shark attacks and ice cream consumption are linked? It's obvious, no, from this figure. Well, in fact, there is a common source, which is the sun, of course. When it's nice weather, people eat ice creams, go to the beach and swim, and have more chance to meet a shark while they are swimming, at least in the Pacific Oceans. Something more serious than that, if you have 2 sinusoids, it's chicken and egg. Which one leads which one? According, if you calculate the cross correlation, which is the classical way to try to find the time lag, if you start with the first one and then the second one, the blue one, and then the red one, or the red one and the blue one, you have or the shift between the two, or the period minus the shift between the two. And it's just impossible to know which one is the cause and which one is the effect. There are other ways to do that. The Granger test is one of the well-known ones. You just see if taking a new time series improves the correlation of the other one. It's a statistical test. Another approach is not to look at statistics and correlations. Somebody said one day, statistics I was a prof of statistics at a given moment. Statistics are like bikinis. They show you a lot of things, not the essential ones, but eventually it can give you some ideas, but it's about that. So you can also look at the structure of the system and trying to find, according to the structure, which are the causes and which are the effects. We will come back to that later on. Now, as I said, the best of IPCC models are the global circulation models, and they are based on local equilibrium and Navier-Stokes equations. So they divide the atmosphere in a lot of small cells. They suppose local equilibrium, and they use the Navier-Stokes equations to describe the transfer of energy, mass, etc. From cell to cell, vertically and horizontally. This requires huge computers, of course, and a lot of money to run that. Now, those are the Navier-Stokes equations in spherical coordinates, just to impress you, don't worry, and to be maybe just dissuasive to try to put your nose in that. And this is the outcome of the game. It's for North America. It's 30 times the same simulation, and this is the outcome of the game. What did they change? Nothing. Yes, one thing. They changed the temperature by less than 1/3 of 1 degree from one figure to the other, and it's completely different. Another proof that the system is chaotic and unpredictable. What are they doing? Cherry picking of what please the thesis. They put that forward and they hide all the rest of the simulation, but that's the reality. In fact, they tackle what's on, that's complexity. Huh? You have on top linear systems, on the bottom nonlinear systems. On the left-hand side bottom, I show you that where the logistic equation is that I used as an example of a chaotic system earlier. But what they are doing, the climate system, is continuum, nonlinear, and you're on the bottom right, the top of complexity. It's very complex to analyze that. And I think they have been a little bit naive. And between climatologists and modelers, you need some system analysts to put some order in the link, in the interface between the two ones. Now, all that to say you that you have to understand the structure of a system before looking at its dynamics, which is common sense, but they forgot that. Yeah, some wisdom, not from Central Asia, from India. But first, some software wisdom. You know, of course, rubbish in is rubbish out. And you know also that with 2 parameters, I draw you an elephant. And with 3, it would even wag the tail. The problem is that IPCC thinks that the tail wags the elephant, but that's another problem, of course. More seriously, it's obvious that if you write an algorithm saying that the temperature must increase when CO2 increase, your model will show you that the temperature increase when CO2 increase. It's as simple as that. It proves nothing else. About experimental data, that's that Indian tale. It's a blind man and an elephant. It's a classical one. I don't know if you know it, but quickly, you have 6 blind men that mess around, holding each other by the shoulder, as we know. And they meet an elephant. And the first one, when he hits the body of the elephant, it's, oh, this is a wall. The second one, he touched one of the defenses of the elephant, oh, this is a spear. And the third one, go and take the tail of the elephant, and say, this is a snake. And the next one, touch the knee and the leg of the elephant, and say, that's a tree. And the other one comes near the ears of the elephant and says, oh, that's a fan, a big fan, what's that? And the last one say the elephant is just like a rope. Okay? Just because you don't have interdisciplinarity. You have climatologists, they don't listen to geologists, they don't listen to oceanographers, they don't listen to physics and to engineers that know a little bit about systems. So, the lessons taken from this tale, let's try to build up a model going to see all what has been said everywhere. The sun dynamics, the moon, cosmic rays, the planetary gravitational forces, electromagnetic fields, meteorites and asteroids, dust, volcanoes and underwater volcanoes, tectonic plates, boundaries, albedo, radiative and convective heat transfer, of course, convective also. Convective mass transfer, and even with CO2. This is the result. Nice, huh? I wouldn't comment it too much because I think Professor Molnar will probably develop that in his talk later on. Something similar, we discussed this together, but this is about the global figure that we have. Now, what can you do with that? Saying, wow, it's complex, forget about it. You can also try to find causes and effects from the structure, as I announced earlier. But first you can see yourself, are those IPCC experts serious? Because they want to reduce this to a simple tuning button. This is crazy, huh? Completely crazy, nonsense, complete nonsense. Now, coming back to causes and things like that, well, in that graph that I showed you, a cause is something emitting one or many arrows, but not receiving other arrows. And an effect is something receiving a lot of arrows. And in between, well, you have the important and nasty, more or less unpredictable guys, if you don't look carefully, that receive arrows, send arrows, and they have a lot of feedback loops. And that's why the system is complicated, because it's like that. So if you look at that, where are the causes? Those are the causes. Those are the only ones having just arrows coming out of it. Okay? And we are the effect, we are where is the critical roundabout in all that? It's there. It's at the interface between ocean and atmosphere. That's the real central roundabout of all the model. That's on what we need to focus and look at its dynamics once we have now a structure of it. Now you can go further with those maps. For example, here I represent a very simple map. Such a map is equivalent to a table where in rows and columns you put the same thing, but you put a 1 at the intersection if the row sends an arrow to the column. This is also a matrix, and then you can crunch the data by matrix analysis, and you can see how far a given concept is a driver or an effect, or somewhere in between, a roundabout, as I call them. You can also identify by multiplying this by itself feedback loops. I have no time to go in detail, and I don't want to teach you about complex system analysis. I put that in appendix of my presentation if you're interested, and we can discuss, of course. So we come to the dynamics, and just focus on the heat balance. You know this one? That's Trendbert updated by Wild in 2013, the global heat balance, with that controversial back radiation from the sky. And here I make reference to some work done by Arthur Rorsch, who was the head of TNO. He's a pioneer, Dutch pioneer of climato-realism, and he's an old friend, and we think together and complot together to bring the truth forward. It's based also on a book by Hartmann, which is 25 years old, and which is probably the best for looking at heat and mass balances and identifying the parameters. So that's the model, okay? Interface, just the skin interface between the ocean or the soil, but the ocean is more interesting because it's 70% of the surface. And you have all the mechanisms that are there. I don't go into details. If we work locally, we can just look at the box and say that globally and locally there is no exchange with neighboring boxes because they are the same if we work very locally. As a starting point, we should see what happens later if this is needed. Now, you can write, well, some people can write, I can do also, I have a background in chemical engineering, the heat balance in such a system, and you crunch the data, and you come to such an equation. No. The change, it's a differential equation written as a difference equation. So an increase in temperature locally is defined by a variable solar flux minus some back radiation or reflection on the clouds. It's the same. Plus terms that describe the convective heat exchange and the latent heat and specific heat associated to it. Okay? So a term changing with time. The radiation term, power 4. More or less linear term and an independent term, 4 parameters for all that. And I just show you here how interesting this is because I take a sinusoid over 5 days, day temperature, night temperature. I approximate it by a sinusoid. And I start from a point, that's a blue curve, far away from that equilibrium situation. So I'm not in balance, I'm not in equilibrium, I'm far away from equilibrium. This comes back to the thoughts of one of my old masters, Prigogine, who was a Nobel Prize for studying such systems far away from equilibrium. And you see that, in fact, this equation, which makes sense, behave like an extremely strong attractor. In less than 1 day or 2 days, a meteor event, some storm weather or some cold in this case, is absorbed by the system, and you come again around what is normal. You never reach an equilibrium. It's a dynamical equilibrium. Against, you have an orbit around an average value. It's chaotic also. Now, we can describe the dynamics locally, and we just need to adjust those parameters. You can do that by hand very easily, or you push on solver on your Excel spreadsheet, and it does that for you. But otherwise, with a few toggles like that, you can adjust that very easily and see the influence of the parameters on the blue curve. It's very easy to do, and I can share this file with you if you want. It's an oversimplified model, of course. We don't have snow and ice melting and other things like that. But it's a good starting point. Now, it's important because I suggest to define the local parameters of such a model locally and not going to the anomalies, because we have seen that we have a lot of trouble when we go to global anomalies. Let's do that locally, that people play with a model like this one, maybe better than this simple model I show you here, and that they try to define locally all the parameters. In the meteor stations, they can do that. And then instead of sending the temperature, average, and things like that, they send the raw estimations of those parameters, changing with time and location. And by data mining on big data, you can find some trends, you can find some causes, effects, and things like that. That's the approach I suggest as a new view on climate change analysis. Okay, now if you take a longer period of time, this simple sinusoid doesn't work, of course. You need to add the 11 years, 60 years, 180 years cycles that are known in solar activity to that. But you can do that, it's not a problem, and the system behaves just in the same way. Now, this is a meteor model based on 4 or 5 days. Is meteor different from climate? That's one of the claims. When it's not going in the direction of IPCC, it's weather. When it's going in the direction, you see it's climate. Well, for example, here that's ice melting. You see there a little spot which is. I would require a little bit more time because I started later than foreseen. So you see that spot, and they say that's weather. Okay, but the system is fractal, and you have a lot of chaotic and fractal things in nature. Don't forget Lorentz, the butterfly effect of Lorentz, which was the rediscovering of chaos theory in the 60s. But you have also some leaves, fougere leaves, for example. I built like that. I built that with a simple mathematical equation. And also the other one is interesting because it really looks like a cut through the Earth. If you look at it, and you see even the effect of the volcanoes, the little emissions that are there. It's just a similarity, that's all, but it's interesting if you think a little bit about it. We know that this, I showed it already, explains that the temperature change from point to point, increase, stabilize, decrease, etc., in a cyclic but non-periodic way with amplitude variations. And we cannot do that with what we know. We need to use more advanced techniques. That's what we need to measure, what we need to detect, and how. Well, the best thing is to use a freeware that I like a lot, which is this one. And I'll show you briefly a few outcomes of it. I take the Vostok data, which is the longest time series we have, so I work on the Vostok data. First, obviously, on the right side, you see the amplitude distribution, showing that it's not a Gaussian bell curve, but you have two modes, which is obvious, the ice period and the temperature period. And that we spend much more time in ice situation than in temperate situation. And then I have to introduce you a concept of phase plan, which is based on Taken's theorem, saying that if you take the value of a function, some time delay from today, and if you make that picture, you obtain a lot of information on the structure of the system, in fact. But you have to find the optimum time lag between what you measure, and also, instead of taking one temperature, you take a string of data, because it's a characteristic feature of the system and it gives better results. This is how you do that, but this is, roughly speaking, how a phase plan will look like. From top left to bottom right, deterministic linear, non-monotonic, linear plus some random noise. You can still predict some trend in the signals. Now, if it's completely random, there is no trend to find, but you can also have a situation where the system is non-linear, and for a given situation, you have 3 possible answers, and then you have the chaotic signal, which is on the right. And if you apply it to Vostok, Ta-da! The signal is chaotic. Obvious. You can find also the periodicities back with recurrence graphs better than fast Fourier transform because the periods are not exactly constant. So this is better. And this is interesting, the correlation dimension. The details I give in the paper, I have no time because I will be hooked off the floor otherwise. But what's interesting is that the correlation dimension, when it's not an integer number, it means that the system is fractal. And you see that all of the numbers in the yellow boxes are not unit numbers, so the system is fractal. And you'll see also that it shifts away from the diagonal for random signals, which is a proof that there is some organization, that there is a chaotic behavior of those data. And then you can take all those strings, put them together, shift it a little bit, and that's what you obtain from left to right, a random periodic signal, some trend line, and some local chaos and random between it. That's what you obtain for a perfect sinusoid. Beautiful, huh? That's what you obtain when you put some noise. That's for the sunspots. It's not completely random. Huh? You see some structure coming in it, so the sunspots have also a chaotic signature. And that's for Vostok dimension, Vostok data. So you see some horizontal lines, which gives you the period of the Milankovitch cycles, of course. Huh? But you see the spots corresponding to the chaotic behavior. If you change the resolution, you see much more the periodic trends than the chaotic behavior. Yeah, I have to skip that. Just to speak on those factors, I cannot do it. Just if you want to 3 more minutes, and then I finish. Just to say that if you want to go to the global picture and link those different cells together, you need to know about the flows, which is very complex. Here you have the flows around the South Pole, for example. How can you characterize that? Well, here comes chemical engineering. They have 2 basic vessels, a well-stirred tank or piston flow, plug flow. And those are the equations. And an infinity of mixers put in series is equivalent to a plug flow, in fact. And this is what happens when you trace different combinations of that with a pulse tracer. So we can identify the structure and the parameters just by injecting some pulses in the system. This comes from Octave Levenspiel, who was my professor in chemical engineering a long, long time ago. So respect to him. Now, in our case, we have probably on the bottom the ocean looking like that, and on top the atmosphere looking like that. And you can have some dead zones and things like that around it. Calculation very easy. You have a state vector giving the parameters at a given moment, a transition matrix, and the next state vector after delta t. Now, I have not so much time to talk about that. There are non-linear methods to see how far you can predict a signal, a given time series. It's based on horizontal visibility. That's the beautiful region where I'm living in the south of France. And they try to put wind turbines there, so you understand that I fight against that, of course. And the idea is, if you look in the direction, how many top of hills can you see? And if you transpose that to the timeline, and if you look on the timeline, how many peaks can you see on the timeline? If it's perfectly periodic, just one, because all it's like at the army, all of them are really on the same level. If it's random, it fluctuates in some way, and if it's chaotic, it fluctuates in another way, and you have chance to see more. So if you do that, you obtain a graph like this one. I took again the logistic equation, and you have the time series on the top, and on the right side, you see that you can predict. You must stay under the dashed line, huh? And you say that you can predict what happens with this chaotic signal for 3-4 items, and then you switch to the unpredictable way. An easy very test, easy very method to show how far you can predict. If you do that to temperature data, if you do that on temperature data, It doesn't work at all. You cannot predict that 1 century as IPCC wants to do it. And last but not least, it's really the end. It's really the end. This is very interesting. Do we need a cause, an external cause, to drive the system? Or is self-organization possible in such a system? Well, you can imagine that at the time there was a climax and one concept sent a signal to the other ones. And then this excited a little bit more the other ones. It's like a kind of porno movie, maybe, or something like that. I don't know. But if it increases less than linearly, as indicated there, and if you take, say, 50 oscillators, sinusoids, with different initial phases, random initial phases, and you run the system for a while, you obtain what's on the bottom, which is a periodic reproduction of the same thing with, or in phase, or with a phase lock, some happening before other ones. And you could be tempted to think that the first one of such a train is the cause. Well, there is no cause, the system influences each other. So the idea is about climbing to the top, flashing, falling down to zero because you are exhausted, and then again starting to be excited. But light flies are working like that, lasers are working like that, and climate is working like that, if you recall this. You see that? When you reach the top value of a cyclic component, it explodes into other ones. I'm sorry, I have to finish here. Thank you very much.